Okay, my name is Junshigam. Today I'll talk about scattering property of atmospheric ice crystals using blue water supercomputing. First, we acknowledge thanks to blue water team member for completing time and the DOE ARM ASR program for funding and Maxim Yurkin and Andres Maki for numerical codes. I'm going to start with why we need this study and why this study is important, and then what kind of problem we have and why we need a supercomputer, and then some results from orientation average and atmospheric halo formation will be shown, and summary will be followed. Okay, here's my motivation. So cloud interact with short wave and long wave radiations, and then to know the role of cloud in climate system, we should know about the radiative property of this cloud. And then what kind of problem we have. So cloud consists of non-spherical and spherical ice crystal, spherical particles. So in terms of thermodynamic phase, cloud can be divided into three categories. First one is a high cold ice cloud. An ice cloud consists of non-spherical particles. And then spherical and non-spherical particles coexist in mixed phase cloud. And then liquid cloud, this one is a low warm cloud, consists of spherical particles. We are focusing on this ice cloud. And then this ice cloud consists of wide variety of non-spherical shapes. And these non-spherical shapes cause lots of problems. Let's see what's the problem. And then first biggest thing challenging is finding a proper method to calculate these scattering properties. First, spherical particles. So usually in a warm liquid cloud, we can use the Meade theory for most of particle size, and then we can use the geometric optics method for large particles. However, for non-spherical particles, it's totally different story. So non-spherical particles, we cannot no longer we cannot use the Meade theory anymore, and then but we can use the geometric optics method for large particles. For small particles, we cannot use this geometric optics method. Geometric optics method doesn't work for small particles. And then for these small non-spherical particles, we need exact solutions such as T-matrix and FDTD and DDA method. Let's see light scattering solutions. So geometric optics method is a very efficient method, and this one is computationally very cheap. However, it is approximation, so that means it's not an exact solution. And then we can use this geometric optics method only for particles much larger than wavelengths of incident light. Usually we define this parameter called the size parameter in the calculation of scattering properties. So size parameter is defined as the ratio between particle maximum dimension and wavelengths of incident light. For exact solution can be applied for small particles. This exact solution is a solve Maxwell's equation, and I just mentioned we have a DDA and FDTD and T-matrix method. However, these methods are computationally very expensive, and computing resources required computing resources increase rapidly with particle size, and then applicability of upper limit is not well known. However, theoretically it is possible with large resources such as blue waters. Okay, so next problem is the size and shapes. This nice figure shows that ice particles in real ice cloud. It consists of various shape and sizes. So we need to calculate that every shapes and every sizes. Next problem is the orientation. The most ice crystals does not have a preferred orientation. So we need to calculate this orientation average to get the mean scattering properties. So we are commonly assume the random orientations. For example, here is the right one is the one type of ice crystal called column, and this nice figure is real ice crystal images, and it shows various orientations. So we need to calculate these various orientations to get the mean scattering properties. Next one is the next problem is the wavelength. As we need to calculate this short wave radiation emitted by sun and long wave radiation emitted by Earth. Since the refractive index of ice crystals vary with these wavelengths, we need to calculate the scattering property of ice crystals across large wavelength ranges. Let me summarize the challenging problem. So I just mentioned that we need large resources to compute these non-spherical particles, and that we should consider various shapes and sizes, and then across the large spectra, and the orientation average is required. We have been using NICS Kraken and TACC Stampede, and then we're facing some problem. For the larger particles, we need much larger resources, and now we are using blue waters. Then using this blue waters, we are building this scattering database. They are very important and fundamental, and that this database is input for radiative transfer model and climate model, and also a satellite retrieval algorithm. To overcome this problem, using blue waters, we decided to use this discrete dipole approximation called DDA. And then in DDA, the ice crystals is represented by small this called dipoles. So ice crystals is consists of n dipoles, and we assigned this n dipoles to the n cores in blue waters. And then we solved McFarquhar equations. And the DDA is very a powerful tool. It can apply to any shape, and it is faster than FDTD. And then now we use the open source code. Is called Amsterdam discrete dipole approximation. Is called ADDA. Okay. This one is an example of orientation average. So this figure shows the scattering phase function and linear degree of linear depolarization and asymmetry parameter and extinction efficiency. So each line or each dot is represent to one orientation. And then this figure shows the wide ranges. And then the question is how many orientation average are required to achieve the accurate calculation. For example, 1.0% of a result. Maybe there's more orientation would be better, but always this calculation resources is limited. So for this calculation, we just use a 10 blue waters node. So each orientation needs 0.5 hours, and then total of 56K node hour is required. So this one is just for one single particle and one size and one wavelength. And then I just mentioned we need to repeat this across large size and shapes and wavelengths. So this one is very expensive. And then question is, can we save this computing time? Yes, we can. So I just mentioned this, we need the orientation average to get the scattering properties such as phase matrix, asymmetry parameter, single scattering albedo, and extinction efficiency, etc. And to define the orientation of ice crystal, we commonly use the three Euler angles. For this study, we choose the two different orientation average scheme. First one is the lattice grid. So lattice grid is equal space the selection of Euler angle. And the second is the more advanced one is called Cosine color method. It efficiently chooses the Euler angle in 3D space. So for this simulation, we choose the 4 different ice crystal models. It's called Gaussian random sphere, and Drexel, and budding buckyball, and column. They are a common crystal shape to represent the small ice crystals. Their size is 10 micrometer. We use the ADDA, and 2 different orientation average method was selected, and then 3 different wavelengths. Let's see, this one is asymmetry parameter of Gaussian random spheres, and this one is the number of orientation. As the number of orientation increased, this asymmetry parameter converts to, and then we put the point plus minus 0.5% line here. So if the asymmetry parameter fall in this between this line, and then it achieved 1.0% accuracy. The blue one is using the quasi-Monte Carlo method, and we read this minimum number of orientation. For example, QMC requires 1152 orientation average to achieve this 1.0% accuracy. Next one is the lattice grid represented by red one, and that it requires much larger orientation average, and that we calculate that this mean number of orientation average ratio. For example, a lattice grid required about 15 times more computing time than QMC. Yes. So this one is showed at 3.78 micrometer, and next one is 0.00 micrometer. So 0.00 micrometer at this wavelength ice crystal is non-absorbing. And compared to previous slide, more orientations are required for non-absorbing wavelengths. Next one is column, same wavelengths, and compared to geometric a Gaussian random sphere, a column is more non-spherical particles, and compared to geometric Gaussian random sphere, it requires more orientation average. From this study, we draw several conclusions, but the most important thing is the QMs can save computing time more than 50%. Okay. Let's switch gear a little bit. So next one is the atmospheric halos. So scattering calculation for small non-spherical ice crystal requires lots of computing time. And then geometric optics method required much less computing times. And then we can use the geometric optics. However, for small ice crystals, we cannot use the geometric optics. So to find this threshold size is very important. You may see this beautiful phenomenon. In this figure, 22-degree halos and 46-degree halos and upper tangent, and the sunducts are shown. 22-degree and 46-degree halo is circular halos, and this one is caused by interaction between sunlight and randomly oriented hexagonal ice crystals. So here, scattering phase function of a column is shown, and that this sharp peak, 2 sharp peak, is corresponding to these 22 and 46 halos. So halo is appear when ice crystals should be very large, and then so finding size at which this ADDA simulation produced halo is that is the threshold size we want to find. For this simulation, okay, so we define the columns with length and width, and then aspect ratio is the ratio between this length and width, and then we choose 6 different aspect ratios. So 0.1 is a thin plate, and 4.0 is the long columns, and then width up to 20 micrometer and length up to 48 micrometer at wavelengths of 0.55 micrometer, and using ADDA and QMC. Okay, so this one is a scattering phase function of a column. The aspect ratio of 0.0. So from left to right, ice crystal size increased. Then here's a black line is the mean scattering property. Then each color represented each orientation. As the small ice crystals doesn't produce these halos, and as the ice crystals getting larger, it produced these 22 and 46 halos. Let's see more detail. We define the halo ratio. So halo ratio is the ratio between 2 different wavelengths. For 22 degree halos, we selected 22 and 18 degrees, and 46 degree halos, we selected 46 degree and 42 degrees. So halo forms when this halo ratio is larger than 1.0, as noted as a broken line in each figure. So in each figure here, we show the 6 different aspect ratio, and there only 42 only size crystals aspect ratio close to 1.0 can produce these 46 and 22 degree halos. And then only the compact shape produce this 46 degree halo, and other ice crystals, for example, aspect ratio of 1.0 cannot produce this 46 degree halos. Let's put this result on the sky. This one is the polar coordinate plot of a scattering phase function. And this column shows the large ice crystals simulated with the geometric optics method, and the 3 different aspect ratio is shown. So this one is what we seen in the sky. And then the center one is the sun, and the bright inner ring is 22 degree halos, and the bright outer ring is 46 degree halo. This column shows the small ice crystals with only 4 micrometer using ADDA simulation, and then compared to large ice crystal, it doesn't have a distinct halo features, and only the diffraction pattern is dominant. Next one is the largest ice crystal simulated with ADDA. And then in this case, we see that these 22 degree halos, and for aspect ratio of 1.0, we see the this 46 degree halos. However, is it quite close to geometric optics simulation, but we need more larger size simulations. Okay, this one is my summary. So QMs can save more than 50 times of computing time. And atmospheric halo forms a size parameter of around 60 micrometer. It depends on aspect ratio of ice crystals. And however, we need more larger simulations. And the scattering, we are building scattering database, and this one is very important and very fundamental, and it has lots of implications. Thank you.